$87. 2 bags of 10-10-10 fertilizer, one in April, one in July. I carried them from the garden center, ripped them open, and scattered every pellet across 6 raised beds and a row of tomatoes. The bags are empty. The receipt is in my kitchen drawer. The question is simple. Where did $87 go? The answer is on the label, except it is not. The label says 10-10-10. 10% nitrogen, 10% phosphorus, 10% potassium. Those 3 numbers sit on every bag in every garden store in the country. They have been there for decades, and they describe something that almost never happens inside the soil. Here is what the label does not say. It does not say how much of that nitrogen will still be there in 48 hours. It does not say what form the phosphorus takes once it hits water. It does not say that potassium, the 3rd number, the one most gardeners ignore, behaves differently depending on whether your soil has clay or sand. The label gives 3 numbers. The soil gives a different set entirely. I want to walk through each of those 3 nutrients, not the theory, the dollars. Because $87 entered my garden in pellet form, and I tracked what came out the other side. Start with nitrogen. It is the first number on the bag, the one most gardeners care about. The one responsible for green leaves, stem growth, and the general look of a plant that seems healthy. A 40-pound bag of 10-10-10 contains about 4 pounds of nitrogen. That costs roughly $21 of the $43.50 I paid per bag. The most common nitrogen source in synthetic fertilizer is urea, small white pellets, water-soluble. The moment those pellets touch moist soil, an enzyme called urease begins converting the urea into ammonium. That part works fine. The problem starts immediately after. Ammonium in warm soil converts to ammonia gas. If the pellets sit on the surface, which is how most people apply fertilizer, up to 40% of that nitrogen floats into the air within 72 hours. Not into the roots, into the atmosphere. I did not know this. I scattered pellets on a Tuesday and watered on Thursday. By then, roughly $8 worth of nitrogen from that one bag had already left my garden as gas. I could not see it. I could not smell it in small concentrations. It was gone. The nitrogen that does not volatilize has a second exit. Rain. A single heavy watering. Any event that moves water through the top 6 inches of soil carries dissolved nitrate downward, past the root zone, into the subsoil, eventually into groundwater. This process has a name: leaching. In sandy soil, a 1-inch rain event can push nitrate 12 inches deeper in a single day. My raised beds have sandy loam. I tested. I buried ion exchange resin capsules at 3 depths, 4 inches, 8 inches, and 14 inches. After 1 week of regular watering, the capsule at 4 inches, the root zone for most vegetable transplants, had captured approximately 35% of the nitrogen I applied. The capsule at 14 inches, well below any roots, had captured 28%. The rest was either in the atmosphere or in the top inch of dry surface soil, baking in the sun and doing nothing. That means of the 4 pounds of nitrogen in one bag, roughly 1.4 pounds stayed where roots could reach. The other 2.6 pounds were either in the air or below the root zone. 65% gone. Not reduced, not diminished. Gone. Physically absent from the place I paid it to be. And it does not disappear quietly. The nitrogen that leaches into groundwater becomes nitrate contamination. The EPA sets the safe limit for nitrate in drinking water at 10 parts per million. In agricultural regions with heavy fertilizer use, well water routinely tests between 15 and 30 parts per million. I am not farming corn on 500 acres. I am fertilizing 6 raised beds. The scale is different. The chemistry is identical. Every granule that passes through my root zone enters the water table beneath my property. The nitrogen that volatilizes enters the atmosphere as ammonia. Ammonia reacts with other pollutants to form fine particulate matter. It also deposits back onto soil and water bodies downwind, contributing to nutrient loading in ponds, lakes, and streams. The algae bloom on the retention pond 3 blocks from my house happens every August. I used to think it was a mystery. Now I think it might be a receipt. There is a third loss pathway I did not discover until I started reading soil science papers. Denitrification. In waterlogged soil, bacteria convert nitrate into nitrogen gas and nitrous oxide. Nitrous oxide is a greenhouse gas, roughly 270 times more potent than CO2 per molecule. If I overwater after fertilizing, which I did every time because the bag says, "Water in thoroughly," I create perfect conditions for denitrification. The nitrogen I paid for literally becomes a greenhouse gas. The bag does not mention this. Now phosphorus, the middle number, the one that controls root growth, flowering, and fruit set. A 40-pound bag of 10-10-10 contains 4 pounds of P2O5, which is not the same as 4 pounds of actual phosphorus. Phosphorus pentoxide, P2O5, is roughly 44% elemental phosphorus by weight, so the real phosphorus content is closer to 1.76 pounds per bag, already less than the label implies. Phosphorus does not leach the way nitrogen does. It has the opposite problem. It does not move at all. The moment soluble phosphorus from fertilizer contacts soil particles, iron oxides, aluminum hydroxides, calcium compounds, it binds. Chemically locks to the surface of those particles. In acidic soil below pH 5.5, phosphorus bonds to iron and aluminum. In alkaline soil above pH 7.5, it bonds to calcium. The result is the same. The phosphorus is physically present in the soil. A lab test will detect it. Plant roots cannot access it. I had my soil tested in March before application. Phosphorus, 18 parts per million. I applied fertilizer in April. Tested again in September. Phosphorus, 31 parts per million. Looks like an increase. Except available phosphorus, the fraction roots can actually absorb, they went from 12 parts per million to 14 parts per million. Almost everything I added was locked up. The soil held it hostage. Research from land-grant universities puts the first-year availability of phosphorus from synthetic fertilizer at 10 to 25%. The rest stays bound. Some of it becomes available over years as microbial activity and root exudates slowly release it. Some of it never becomes available within a human lifetime. I paid for 1.76 pounds of phosphorus. Approximately 0.26 to 0.44 pounds reached my plants in the season I applied it. The rest is sitting in my soil, visible to a lab, invisible to a tomato. There is a narrow pH window, roughly 6.0 to 7.0, where phosphorus is most available to plants. Above or below that range, lockout increases sharply. My soil pH when I tested, 5.7. Slightly acidic, enough to push phosphorus availability toward the bottom of that 10 to 25% range. I did not test my pH before buying fertilizer. The bag did not suggest I should. It said, complete nutrition for all gardens. My garden's pH made 80 to 90% of that phosphorus inaccessible the moment it dissolved. Complete nutrition, incomplete delivery. I spoke with a county extension agent about this. She told me that, in her experience, most home gardeners never test soil pH before fertilizing. They buy what the label recommends, apply at the recommended rate, and wonder why their peppers have blossom end rot. Blossom end rot is a calcium deficiency. Excess phosphorus in the soil competes with calcium uptake. The fertilizer they bought to fix the problem may be causing it. She said this happens constantly, every spring, the same phone calls. Potassium is the third number, the one least discussed and least understood. Potassium controls water regulation inside plant cells, disease resistance, and fruit quality. Of the three macronutrients, potassium is the most mobile in soil solution. In theory, it should be the easiest one to deliver. In practice, clay soils grab potassium and hold it between mineral layers. The technical term is fixation. Heavy clay can fix 50 to 70% of applied potassium within days. Sandy soil loses potassium the same way it loses nitrogen, straight down with water. My sandy loam sits in the middle. I estimated roughly 40 to 55% of applied potassium reached the root zone and stayed there long enough to matter. Better than nitrogen, better than phosphorus, still less than half. There is a fourth category the label does not address at all: micronutrients: iron, zinc, manganese, boron, copper, molybdenum. Plants need tiny amounts of each. Without them, photosynthesis slows, fruit quality drops, disease resistance weakens. A 10-10-10 bag contains 0 listed micronutrients. None. The label does not mention them because the label only guarantees what the manufacturer puts in. What the manufacturer puts in is the cheapest blend that can legally carry the 10-10-10 designation. The micronutrients most garden plants need were never in the bag. Healthy soil with active biology provides micronutrients through mineral weathering and organic matter decomposition. A single tablespoon of biologically active compost contains more micronutrient diversity than a 40-pound bag of 10-10-10. The difference is that nobody sells micronutrient-rich compost in a branded bag with a guaranteed analysis. There is no margin in it. Add it up. One bag, $43.50. 4 pounds of nitrogen, 1.76 pounds of phosphorus, roughly 4 pounds of potassium. After volatilization, leaching, phosphorus lockout, and potassium fixation, my plants received approximately 1.4 pounds of nitrogen, 0.35 pounds of phosphorus, and 2 pounds of potassium. I applied this twice, 2 bags, $87 total. The value of the nutrients that actually reached roots, priced at what a precision liquid fertilizer would cost to deliver the same amount directly to the root zone, comes to about $2.60. I have the spreadsheet. I have the soil tests. $87 in. $2.60 of actual plant nutrition out. That is a 97% loss if you measure by dollars. Approximately 70% by weight of applied nutrients. Either number should be printed on the label. Neither one is. There is a detail that makes this worse: timing. Synthetic fertilizer delivers its entire nitrogen load within 2 to 6 weeks, all at once. Plants do not need all their nitrogen at once. A tomato plant needs small, steady amounts across 90 to 120 days. Dumping 4 weeks of nitrogen into the first 2 weeks means the plant gorges early, pushes foliage at the expense of fruit, and then runs out of available nitrogen right when fruit is setting. I saw this on my own plants: huge, leafy tops in June, small, pale tomatoes in August. I tracked this in 2023 with tissue tests on my San Marzano tomatoes. Week 2 after fertilizer application, leaf nitrogen at 5.8%. Optimal range is 3.5 to 4.5%. The plants were overdosed. Week 6, leaf nitrogen at 2.1%, below deficiency threshold. The plants went from excess to starvation in 4 weeks. I was standing in the garden holding 2 lab printouts, one from June and one from July. trying to understand how a fed plant could be starving. The answer is that I did not feed it. I dumped a month of food in its lap and walked away. Think about what this means for flowering. Tomatoes set fruit when nitrogen is moderate and phosphorus is available. High nitrogen during vegetative growth tells the plant to keep making leaves. The plant follows instructions. It makes leaves. Gorgeous, dark green, enormous leaves. The gardener thinks the fertilizer is working beautifully. By the time nitrogen drops and the plant shifts to reproduction, the growing season is 6 weeks shorter than it needed to be. I blamed the variety. I blamed the weather. The real cause was $43.50 of mismatched timing. Slow-release synthetic fertilizer exists. It costs 2 to 3 times more per pound of nutrient. The coating that slows the release is a polymer, plastic in most cases. It breaks down into microplastic particles in the soil. I switched from standard to slow release for 1 season. The nutrient efficiency improved to maybe 40% delivery. The plastic stayed. I want to talk about a system that delivers nutrients at close to 98% efficiency. 0 cost, 0 plastic, 0 bags. It has been running for about 400 million years without a product recall. Walk into any forest. Stand still. Look down. The floor is brown, tan, dark in places. There is no fertilizer bag in sight. There is no NPK label. There is also no nutrient deficiency. The trees are 60 feet tall. The ferns are deep green. The soil, when you dig into it, is black, crumbly, and smells like wet earth after rain, a scent called geosmin, produced by soil bacteria in the genus Streptomyces. That smell is the signature of a living process. A forest cycles nutrients in a closed loop. Leaves fall. Fungi break them down. The technical term for the network of fungal threads in soil is mycelium, and in forest soil, 1 cubic inch can contain 8 miles of hyphal threads. Mycorrhizal fungi attach to tree roots and trade phosphorus for carbon. The tree feeds the fungus sugar. The fungus feeds the tree phosphorus. Neither loses anything. The transaction is bilateral and continuous. Nitrogen in a forest does not come from a bag. It comes from decomposing organic matter released in tiny, steady amounts as bacteria digest it. Exactly when the roots need it, exactly where the roots are, exactly in the form roots absorb, ammonium and nitrate, at a ratio that depends on local soil pH and microbial community. No human designed this cycle. No label describes it. It runs at approximately 95 to 98% nutrient retention. The 2 to 5% that leaks is replenished by atmospheric deposition and weathering rock. The balance sheet closes. I stood in the woods behind my property with a soil probe in June last year. I pulled a core 8 inches deep, dark brown all the way down. I could feel the moisture when I squeezed it, cool, damp, like a wrung-out sponge. Visible white threads of mycelium through the top 4 inches. The smell hit me before I even looked at it. That thick, sweet, earthy scent. I pulled a second core from my raised bed 30 feet away. The soil was lighter, drier. No visible fungal threads. The smell was flat, mineral, dusty, nothing alive. Same property, same rain, same sun, different systems. The forest delivers nutrients for free because it built the delivery infrastructure over centuries. Fungal networks, bacterial communities, organic matter that decomposes at the right rate. The fertilizer bag skips all of that. It dumps soluble chemicals onto a surface that has no biological infrastructure to hold them, like pouring water onto concrete and expecting it to soak in. I stopped buying fertilizer in the spring of 2024. Not because I read an article, because I did the math. $87 for $2.60 of delivered nutrition is not a bargain. It is not even a transaction. It is evaporation with a receipt. What I do now costs less and delivers more. The shift was not dramatic. I did not buy a special setup or follow a 12-step program. I made 3 changes. First change: compost. I built a 3-bin setup from pallets I collected behind a furniture store. Cost: $0. The design is simple. 3 bays, each roughly 3 feet by 3 feet by 3 feet. 1 bay filling, 1 bay cooking, 1 bay finished. Kitchen scraps, garden waste, leaves from the street in October, shredded cardboard, coffee grounds from a local cafe that gives them away in 5-gallon buckets. 6 months of decomposition produces roughly 200 pounds of finished compost per year from a household of 3. I tested it at a state lab. Nitrogen, 1.5 to 2%. Phosphorus, 0.5 to 1%. Potassium, 1 to 1.5%. Lower numbers than the fertilizer bag. That comparison is meaningless. The difference is that 80 to 90% of those nutrients reach the root zone, because they are bound in organic molecules that release slowly as microbes digest them. The same mechanism the forest uses. No spike, no crash, no leaching, no volatilization. The compost also adds something the bag cannot: structure. Organic matter in compost holds water at 6 to 8 times its weight. It creates pore space for air. It feeds the microbial community that makes all nutrients more available. One application of compost does more for soil function than a decade of synthetic fertilizer. I know because I have soil test results from both periods. The fertilizer years. Organic matter steady at 2.8 to 3.1%. The compost years, 3.1 to 5.8% and climbing. The soil got darker. It smelled different. When I dug in April, I could hear the earthworms, a quiet, wet, shifting sound beneath the trowel. That sound was absent 2 years ago. Second change. I kept leaves on the beds over winter. 8 to 10 centimeters of shredded oak leaves, applied in November, partly decomposed by April. By the time I planted, the leaves had become a thin layer of dark organic material on the surface. Underneath, earthworms had pulled fragments into the top 4 inches. I counted 14 earthworms in 1 shovel of soil in April 2025. The year before, with fertilizer and no leaf cover, I counted 3. Earthworms are not decorative. Each one processes its body weight in organic matter daily and deposits castings with 5 times the nitrogen, 7 times the phosphorus, and 11 times the potassium of the surrounding soil. Concentrated right at root depth, free. The leaf mulch also does something no fertilizer can replicate. It feeds fungi. Fungal hyphae break down lignin and cellulose in leaves and wood chips. As they digest, they excrete organic acids that slowly dissolve mineral particles in the soil, releasing phosphorus, iron, zinc, and other micronutrients in plant-available forms. This is the mechanism the fertilizer bag bypasses entirely. The bag delivers nutrients in soluble ionic form. The forest delivers them through a biological intermediary that regulates the pace. One method floods, the other one drips. My plants prefer the drip. I want to be specific about the leaves because people always ask. I use oak and maple. I shred them with a lawnmower. Whole leaves mat down and block water. Shredded leaves settle into a loose layer that breathes. I apply them 8 to 10 centimeters thick in November. By April, the layer has compressed to about 3 centimeters. The rest has been pulled underground or decomposed. The surface is dark, moist, and smells like a forest trail after a warm rain. That smell, damp, almost sweet, with a faint mushroom note, is the clearest sign that fungal decomposition is active. When the soil under the mulch smells alive, it usually is. Third change. I planted crimson clover as a cover crop in September, after the last harvest. Clover is a legume. Rhizobium bacteria colonize its roots and convert atmospheric nitrogen into plant-available ammonium. The air above every acre of land contains approximately 35,000 tons of nitrogen. It is the most abundant element in the atmosphere. The only bottleneck is getting it into the soil. Legumes solve this. No factory, no energy input, no bag. When I cut the clover in April and let it decompose on the surface, it releases roughly 80 to 150 pounds of nitrogen per acre. My garden is about 1/10 of an acre. Roughly 8 to 15 pounds of nitrogen delivered slowly at root depth with no bag, no receipt, and no loss to the atmosphere. The clover seed cost me $6. I want to add a detail about the clover that surprised me. When I pulled a clover plant in March to check the roots, I could see the nodules, small pink lumps, each one about the size of a peppercorn, clustered along the root hairs. The pink color means the rhizobium inside is active. If the nodules are white or green, the bacteria are dormant. Mine were pink. I sliced one open with a pocket knife on the back step. The inside was dark reddish pink. Leg hemoglobin, a protein structurally similar to the hemoglobin in human blood. It regulates oxygen around the nitrogen-fixing enzyme. I sat there holding a plant root that manufactures its own fertilizer using a molecule related to the one carrying oxygen through my veins. $6. And it builds soil structure while it works, because clover roots penetrate compacted layers and create channels for water infiltration. When the roots decompose after cutting, those channels remain. Free aeration, free drainage, no tiller required. Let me rerun the numbers with the new approach. Compost, $0. Leaves, $0. Clover seed, $6. Total annual input cost, $6. Approximate nitrogen delivered to root zone, 10 to 18 pounds. Approximate phosphorus delivered, 2 to 4 pounds. Approximate potassium delivered, 3 to 5 pounds. All released over 90 to 120 days, matching the plant uptake curve. The old way, 2 bags of 10-10-10, $87. Nitrogen delivered to roots, approximately 2.8 pounds. Phosphorus delivered, approximately 0.7 pounds. Potassium, approximately 4 pounds. All released in a 2 to 6 week pulse that mismatches plant demand. $6 delivered more than $87. Not slightly more, 4 to 6 times more nitrogen, 3 to 5 times more phosphorus, similar potassium. And the $6 approach builds soil biology. It creates the fungal networks, the bacterial communities, the worm populations that make next year even better. The $87 approach does the opposite. Concentrated salts suppress mycorrhizal colonization. The 2019 study by Thurkel, Cameron, and Hodge found that high phosphorus from synthetic fertilizer reduced mycorrhizal root colonization by 32 to 48%. The more fertilizer I added, the less my soil could feed itself. I was paying to destroy the infrastructure that would have worked for free. There is a word for a product that solves a problem it creates. I have heard people call it a racket. I call it a business model. The fertilizer industry is not lying on the label. 10-10-10 contains 10% nitrogen, 10% P2O5, and 10% K2O. That is technically true. What the label omits is what happens after the bag opens. The volatilization, the leaching, the lockout, the timing mismatch, the suppression of the biological systems that could do the job better. The industry knows this. The research is not hidden. Land-grant universities have published nitrogen volatilization data since the 1970s. Phosphorus lockout has been documented for over 50 years. The information sits in extension bulletins, peer-reviewed journals, and soil science textbooks. None of it appears on the bag. The bag says, feeds plants for up to 3 months. Under controlled laboratory conditions with perfect soil moisture, ideal pH, and precise incorporation depth, that claim is defensible. In a real garden with surface application, variable weather, and untested soil, the claim describes a scenario that rarely exists. I called a customer service number on one of the bags, asked a straightforward question. What percentage of applied nitrogen reaches the root zone in average garden conditions? The representative paused. Then she said, "Our product is formulated to provide balanced nutrition when used as directed." I asked again. She transferred me. The line went dead. The label says guaranteed analysis. It does not say guaranteed delivery. My neighbor asked me last month why I stopped buying the blue granules. I showed him my soil test results from September. Organic matter up from 3.1% to 5.8% in 2 years. Available nitrogen comparable to his fertilized beds. Available phosphorus higher than his. Earthworm count 4 times his. He looked at the numbers for a while and said nothing. Then he asked where I got the clover seed. I did not convince him with philosophy. I did not tell him nature is better. I showed him a spreadsheet and 2 soil tests. The numbers did the talking. They usually do. If you have a bag of fertilizer in your shed, pull it out this week. Read the guaranteed analysis on the back. Then multiply the nitrogen by 0.35. Multiply the phosphorus by 0.2. Multiply the potassium by 0.5. Those are approximate delivery rates to the root zone for surface-applied granular fertilizer in average garden soil. That is what your plants actually receive. Run your own dollar figure. See if it matches the receipt. I ran mine. The number was $2.60. I remember standing in the garden with the calculator and feeling the grit of dried fertilizer granules under my boots. Crunching. Like tiny promises that never arrived, there is one more thing. The forest floor I tested has never been fertilized. Not once. Not by anyone. The earthworms do not read labels. The fungi do not need guaranteed analysis. The leaves fall. The cycle continues. The nutrients reach every root. 400 million years. No receipt. No loss. Tomorrow, I grew 23 different crops last year. I weighed every single harvest. Only 7 were worth my time. The data might change what you plant this spring.